And yeah, we directly start with the first presenter, which is Lorenzo Santi. And he will talk about multi-material polymeric interlayers. So Lorenzo Santi got his degree in mechanical engineering at University of Parma in October 2022. He started his PhD program in industrial engineering in November 2022 in collaboration with Curie America. The topic of the PhD program is the viscoelastic behavior of interlayer and the influence on laminated glass structures.
Hello everyone. The topic of the presentation and the research is about multi-material polymeric interlayer. And what is a multi-material polymeric interlayer? Usually we are all used to know interlayers for laminated glass application as a single foil between two glass plies that keeps them bonded together. But actually it's much more common nowadays to use interlayers that are composed by different materials. For example, because each interlayer will enhance a different kind of characteristic. For example, if you are more interested in enhancing acoustic performance of the laminated glass or enhancing the optical properties, increasing the mechanical strength, it's possible to combine different types of interlayers between each other to create one single interlayer that have this kind of characteristic. From the mechanical point of view, it's getting a little bit complicated because each material will have its own relaxation function. A relaxation function is a curve, here represented for 3 different materials, that represent the stiffness trend in time of the material itself. And as you can see here, we have 3 different materials, the stiff PVB, centric glass, and acoustic monolayer PVB. And all of those 3 materials have completely different behavior in terms of mechanical properties. So by combining them together, we need to understand the overall mechanical behavior of the interlayer. And this is a little bit complicated. So any finite element model requires as an input data the relaxation function. The classical way to interpolate the experimental points from DTMA is using the Prony series. Prony series is a summation of exponential terms. This kind of approach is widely used, but the problem is that required a lot of parameters to calibrate, and the calibration is not easy. It requires an algorithm ad hoc written for the curve. A novel approach that we are proposing is to interpolate the experimental relaxation function using power laws. Here is an example of a relaxation curve and their experimental points. We can imagine in dividing the temporal branch in different parts. And each temporal branch is fitted by a power law, which in the bilogarithmic graph become aligned. The interesting part of this kind of approximation is that within each temporal branch, we can use just 2 parameters. So one is alpha, which describes the slope of the line within a certain temporal branch, and the other one is C alpha, which indicates the stiffness within this kind of temporal branch. The overall relaxation function becomes then a piecewise function of these power laws. In this kind of case, we have that we can use a geometrical interpolation to obtain the 2 parameters. So this is much easier than using an algorithm that usually it's not always available. And we need to calibrate much less parameters. In the example that I've showed before, we had 15 parameters to calibrate. Instead here, in this kind of examples, is just 6. And for the numerical analysis, this is much more convenient. Okay, about multi-material interlayer. Here is the case that we are going to analyze in this research. This example showed here is we have an interlayer composed by 2 different materials. One of them is used as a core layer, and the other one is used as a outer layer. Usually, the core layer is a softer material, for example, acoustic, and the outer layer could be a stiffer one, but also the reverse. We can simplify this model. Here show how. If we have that these laminates is only subjected to shear load, we can imagine to have still two materials, but we can incorporate the two foils in only one, because we have that the full deformation is calculated by the summation of the two deformation of the two materials. So, and then we can simplify in this way our model. And here we are going to compare the deformation in this first case with this other example. In the first case, we are going to use the relaxation function of the two materials separately. And we are going to calculate the full deformation by summing up each deformation of each layer. In this kind of example, we are going to use one single layer with one single relaxation function. This relaxation function has been calculated experimentally using DTMA analysis by combining the interlayer with different materials. So this is like having a relaxation function. This is telling us the mechanical properties experimentally calculated of the multi-material interlayer. We are then expecting that the two deformation will be almost the same. Not maybe completely the same, because we will always have some kind of uncertainties due to the experiments procedure and the simulation itself, but we are expecting a common trend. Okay, we are all used to know elastic solids, where the deformation and the stress are connected by a derivative of order 0. This is the case of any elastic materials. From the other end, we have purely viscous material, where the stress and the deformation are connected by the first derivative. In our case, we are talking about viscoelastic material. So we are expecting that the stress and the strain is something in between those two cases. In fact, we are going to talk about spring pots, which is a mathematical tool that connects the stress and the strain with a derivative of the order intermediate between 0 and 1. So it could be, for example, 0.3, 0.7. It's an intermediate behavior between spring and dashpot, pure elastic and purely viscous. So we are going to model our viscoelastic polymeric interlayer in this way. So yeah, this is how the constitutive equation of our materials will look like. And here is our problem schematized in this way. In the first case, on the left, we have two spring pots in series. So we can have that the final deformation of our material is calculated by the summation of each deformation of each spring pots. And on the other hand, we have that we only have one single interlayer, and the relaxation function of this interlayer is calculated as we talked about previously. So we are going to compare these two different mathematical schemes. Here is a representation of the relaxation function that we are going to use for the numerical calculation. We are going to consider two different materials. The material R1 used as a core layer is stiff PVB in this example, and the one used as an outer layer is acoustic monolayer PVB. And Rm in this case is the relaxation function calculated by combining the two materials experimentally. Here is showed the experimental points of those in those three cases and their interpolation using the power laws. So it's possible to see here how the power laws can well interpolate the experimental points. And we are going to analyze it in 3 different temperatures. So in order to solve the mathematical scheme that I previously presented, it has been used a finite element model written in MATLAB or Python, because it's not possible to implement yet fractional derivatives and this power law approximation inside the commercial software. So it has been written a finite element model only for solving this kind of problem. The starting point is the relaxation function of the two materials, the material 1 and the material 2. Then we calculate the deformation using the finite element model. So, and once we have the deformation, we can then calculate the stress of the material. It's important to mention that the final stress is equal between the two spring pots. And then once we have the stress, we can do a reverse passages and calculate the relaxation function of the two materials, of the multi-material interlayer, using this kind of relationship, which is the Boltzmann superposition principle. We can calculate the relaxation function RT by reversing this equation. This is the procedure inside the finite element model. Now, this is the concept of for validation of the overall research. We start from the two cases that we have talked about before. So, the two relaxation function for the two materials and the relaxation function of the multi-material. We put it inside our finite element model in two cases, and we obtain the deformation. So our finite element model will give us the deformation in the two cases. The first one, where we are using as an input data the two relaxation function of the two separate material. And the second one, when we are using the relaxation function of the two materials combined together. And we are going to obtain the deformation in those two cases. And we are willing that those two deformations should be approximately the same. If it is the case, we are happy. Here is the result. We have that in those two cases, the trend, as mentioned before, is very similar. Not completely similar, because for sure there is always a certain amount of uncertainties in the interpolation and the experimental calculation of the relaxation function, but we are happy because the trend is very similar. But now we need to validate the model and then calculate the relaxation function. That is the point of the research. Now it's just to see if our model is producing reliable results, so if we can trust it. But now we need to calculate the simulated relaxation function. And this is how we are evaluating the mechanical properties. So we first start from the relaxation function of the two materials. We use it in our finite element model. We calculate the relaxation function of the multi-material, and we need then to compare it with the experimental points. If they are equal, still our model is validated. And here is the result. We have that the dashed black line is the simulated relaxation function. Instead, the experimental point represents the relaxation function of the multi-material if we put it inside the DTMA. We extrapolate this right triangle. We can see here that we have a good agreement between the experimental point and the simulated relaxation function for three different temperatures. So we might be happy because of that, because the agreement is fine. For a quick and dirty result, we might use an elastic model, for example, where the relaxation function has an intermediate values between the one used, of course, by scaling with the thickness of the two material. This elastic model, for real, works pretty well in the early stage of the simulation. But then, with time, the results become more and more divergent between the finite element model implemented. Why? Because in the finite element model is implemented a full viscoelastic behavior of the material. full viscoelastic behavior means that the actual state of stress of the material does not only depend to the actual values of the relaxation function, but it also depends to the previous state of stress of the material. That's why in the early stage we have a good agreement between the elastic model and the experimental points. But with time, those two results are getting more and more divergent. It's possible to see, for example, here, where the elastic model is represented by the yellow line. Instead, the black line is still the simulated relaxation function using a full viscoelastic analysis. And the agreement is even better for higher time, yes. Now, as a last example, just to show you the potentiality of this kind of finite element procedure, has been considered two different cases. The first one, where we have the two materials already considered, and the second one, where instead of Trosifol extra stiff Pro, we are substituting it with, for example, Centriglass. And we are evaluating the mechanical performance in those two cases. So we need to understand if it's convenient to substitute Centriglass with Trosifol Extra Stiff Pro, if there is any kind of convenience in the mechanical performance of our multi-material interlayer. We can see here that at 20 degrees, the blue curve, there is a blue curve, but it's very overlapped with the black curve, which is the first case. So at 20 degrees, we don't have really a good advantage in substituting Centriglass. But we can see that at 40 degrees, the blue curve is much more stiff than the black curve. So in this case, we can see that Centriglass is having a good impact on the multi-material at higher temperature. Instead, at lower temperature, the behavior of the two stacks are equivalent. Now, here I presented a use case where I substitute the material with another one. But we can also, for example, vary the thicknesses or using more material, and we can evaluate in this way, simulating the relaxation function. Now, we are close to the end. So just to wrap it a little bit up, the work has been implemented a new way to interpolate the relaxation function of the polymeric material using power laws, which is convenient because the mathematical treatment is directly connected to the constitutive equation. And then, using the finite element model, it's possible to evaluate the mechanical performance of a multi-material interlayer. And also the prediction is reliable with the experiments. We can also use this kind of results to optimize our problem and to evaluate if the mechanical behavior will be convenient or not. Okay. Thank you very much for your attention. It's over.